Good morning. We will consider some topic related to the Feynman-Katz formula. Okay. So let x t and s t t s x be progressively measurable Markov process in the phase space x b and let v s x s x be the measurable function whose values are complex numbers. We are going to consider some functionals of this process of the following type: integral from s to t v of tau x of tau to tau. Under our assumptions, this is a random variable, an MST measurable random variable. Okay, and we will deal with the following expectations: s x exponent integral v tau x of tau to tau. I formulated one proposition in my last lesson about a sufficient condition when this expectation is finite. It is not difficult to see the absolute value of that exponent. Is equal to exponent integral real part of the function v tau x of tau tau, and this is less than or equal to exponent integral this real part real part with the sign plus. Where v plus is equal absolute value of v minus p plus minus p. Okay, and if this function real part of v tau x plus satisfies the condition of our proposition, then this expectation of this exponent is finite. Moreover, it is supremum over all x expectation, as x of this exponent is finite.
Excuse me? P plus means the positive part of the function.
Yes.
But then you need to divide by 2, maybe.
Oh, yes. Thank you.
Sorry, again, what is the condition?
The condition, okay, I
Just briefly.
I will make some more strong condition on our function v, but I would like to recall that if that function is non-negative, is non-negative values, okay? So if I have a non-negative function, and I consider integral over O x as x tau y v tau y integral over O x over the interval st tau, and I consider supremum over OX from X and supremum over OS T minus H T and supremum over OT from 0 to t. Okay, and if this expression, the limit of this expression as h goes to 0 is less than 1, then we solve the expectation of x exponent integral v tau x of tau can be estimated by some constant that depends on this t. Okay, and this estimation is valid for all x in our phase space. So you see, if this function is such that this condition is fulfilled, then that expectation is finite, and we can consider, of course, this estimation is only on the function, on this function, okay? But there are some integrals. Imaginary part of v tau x tau d tau and integral real part of v tau x tau d tau. Okay, with a sign minus. These integrals should be well defined as well. Okay, so I will pose some more strong condition on the function v. Namely, I suppose that integral over x v tau y p s x tau y is less than some constant t minus s to the power minus gamma. And this inequality is true for all s less than tau less than t, for all x from x with some constants a, t positive, and gamma from this interval. For example, if v is a bounded function, so this integral is not greater than norm v. Norm v is supreme, maybe t. that is supremum over OSX 0t cross x. So in this case, gamma is equal to 0. Yes, maybe if V is not bounded, maybe there is some singularity if tau is close to S. Okay, and if this inequality is valid, then the absolute value of B satisfies the condition of that proposition. I have just formulated. So, yes, because if I integrate, gamma is less than 1, we can integrate it. This inequality, and we will have estimate integral from S to T with tau integral from X. Yes. T over 1 minus gamma minus S to the power y 1 minus gamma. So this is a for such S and T is some constant. Oh no. You see, if I write down here those supremums, okay, so I will see that those supremums goes to 0 if T minus S goes to 0, H, T minus H, T minus S less than H, and if H goes to 0, it goes to 0, I think. So the conditions of that proposition is fulfilled, and I can assert that this expectation here is absolute value of the written. I can write down here supremo over OX and over OS P T. This is a finite number. Okay. Now I am going to prove the following assertion. Suppose that B is such as I draw here. Okay, and we consider the following function PV of S X T gamma. Let this equal expectation indicator exponent integral from x t v of tau x of tau v tau. So this is, it is not difficult to see that this function is something like measure with respect to this argument. So P S X T gamma is equal to the sum of K P V S X T gamma K if gamma is equal to the sum of K and gamma K and gamma K with empty intersection with empty. Okay, and our assertion is as follows theorem. Under that condition, on the function v, I would like to write down one more. V tau x y p s x tau dy is less than constant t minus s to the power minus gamma. Gamma from 0 to 1 and K is the positive. Under this condition, this function PV Sxt gamma satisfies each one of the following pair of integral equations.
And we include one here.
Oh, excuse me. It's not true.
Do we assume now that V is real value or complex value?
Complex value.
So absolute value of this integral or absolute value of
Oh, yes, yes. Thank you. Thank you. This was my assumption. Okay. And under this assumption, we have the following pair of equations for this function PV. PV S X T gamma is equal P S X T gamma plus integral C S X tau y G tau y E V tau y T gamma. First one and the second one. E V S X T gamma is equal P S X T gamma plus integral integral P V S X tau y V tau y P tau y gamma. So if we consider our process on a finite interval of time, so here S is less than T, less than T capital X is a point from our phase space, and gamma is a measurable subset of X. How to prove this theorem? The first equality is a consequence of the following identity. X integral from X to T V tau X of tau v tau equals 1 plus integral v tau X of tau X integral from tau T V tau prime X of tau prime d tau prime d tau. Right, this is an identity. You see, we have on the left-hand side a function that is absolutely continuous with respect to s. And the same function is on the right-hand side of this equality, okay? So if a derivative that must exist for almost every point tau, okay? So I have here the same derivative as this, derivative of this function, okay?
Derivative with respect to s.
S, with respect to s. Okay, so if these functions have the same value at one point, then these functions are identically equal each to the other one. Okay, but if s equals 0, we have here one and here one. Okay, this is an identity. Okay, and now I would like to multiply this equality by indicator. Okay. And calculate the expectation of the expression in the left-hand side and the right-hand side. Okay. So in the left, on the left-hand side, I have here PV. Okay, and here the first item will be this one, okay, and we have the expectation integral tau x tau, and here I write down and the expectation tau x tau indicator x over t x integral from tau to t tau prime x tau prime d tau prime and then tau.
Sorry, I'm a little lost. Where does this indicator of gamma relates to? Where the expression begins?
This I calculate. I am calculating now this expectation multiplied by indicator.
Ah,
This integral. Okay, the first.
I see.
The first. This one and this one we have already obtained. Okay, and now I calculate this expectation of this expression multiplied by indicator.
Thank you.
So I have just used the following formula. C eta is equal expectation eta expectation tau x of tau c, where c is m tau measurable and eta is m maybe is measurable and eta is ms tau measurable. Okay, and I can write down this formula for any c and eta non-negative. In the sense, if some expectation is infinite, then the other one is also infinite. Okay. So if c and eta are non-negative, then we can write down this formula anyway. Okay, and here we have exactly this situation. This is eta, and this is eta, and this is c. Okay, and I know that absolute value of this exponent is finite, and it does not depend on x of tau. That is some constant. So I can write down this formula, and now this is nothing else but this expectation is nothing else but PV of tau x tau t gamma. Okay, so the expectation of this expression is expectation of v tau x tau PV tau x tau t gamma d tau. And that expression can be written exactly in this form. Okay? Now let us prove the second equality. Now we start from the following identity. This integral write down as integral from s to tau. And again, this is an identity because the derivative of this function with respect to t is the same as the derivative of this function with respect to t. So multiply this equality by indicator e gamma x of t. We have here on the left-hand side this function, on the right-hand side this indicator gives us this item. And now we have to calculate the following expectation. Integral v tau x tau e to the power integral from s to tau v tau prime x tau prime v tau prime indicator x of t d tau. And now I use the same formula. This is eta, and this is xi. And according to that formula, it can be written as follows. Integral v tau x tau e to the power integral from s to tau v tau prime x tau prime e tau prime and here and tau x tau indicator x of tau d tau. Okay, and this expectation is nothing else but this transition probability. And we have integrate with respect to this measure, not measure, but sigma additive function with respect to gamma. We have integrate with respect to that measure, generalized measure, a function of tau x of tau. A function multiplied by this exponent. Okay. This is the f of tau, and this exponent, this is exactly integral with respect to this generalized measure, and we have this equality. Okay. Now, let us make the following observation. If transition probability P has identity with respect to Lebesgue measure, or let X be RD, and suppose that P S X T gamma is integral G S X T Y dy, where G S X T Y is the fundamental solution of parabolic equation is given vector field ASX and operator field BSX, such that they satisfy the conditions of the existence of fundamental solution. So in this case, you see PV is also absolutely continuous with respect to gamma. And we know that this function is continuous with respect to all its arguments, okay? So we can expect that PV is also integral of a function G, maybe GV S X Y Y. And we have a pair of equations for this function. Let us write down. G V S X T Y is equal to G S X T Y plus integral G S X tau Z G V tau Z T Y V tau Z V Z. And the other one is X T Y equals G S X T Y plus the tau integral G S X tau Z G S G tau Z T Y tau Z Z. So we can try to solve how to solve these equations.
And perhaps let's do this after the break. It's the time you asked me to.
Okay, thank you. Let us make a little break. Let us continue. So I have just written these equations, and if you can find out a solution to each one of those equations, then we can obtain the following formula. The expectation of phi of x of t, this exponent, is integral phi with this density. Okay. I would like to say a few words about how to solve each one of these solutions, these equations.
May I ask a question?
Yes.
So if we know that EV satisfies this equations below, and we hope that EV has a density GV. So
Yes.
if we prove existence and uniqueness of this, if we prove uniqueness, because we have already known that EV satisfies this equation, then and if we prove that there is existence for equations above, then we have equivalence of that and this.
You see, if this condition probability is absolutely continuous, has a density G, okay, then from this equality follows that PV is also absolutely continuous with respect to gamma. Okay, so we
But we don't know modification.
but there are some problems with that density, because it can exist only for almost every point y, and there is some exceptional set that depends on s, x, and t. Okay, so if we can solve this equation and prove that this is a continuous function with respect to all its arguments, yes, this is, if this is a fundamental solution, it is continuous. If you solve and obtain a continuous function, then you can integrate it with respect to y, and you receive this equation.
Yeah, but we must have uniqueness of that. Maybe because
Yes, I'm going to talk about how to solve this equation.
so uniqueness for equations below plus existence of nice solution
Yes.
of equation above
Yes,
give us equivalence of these two systems.
yes, yes. And how to solve, for example, the first equation. The method of successive approximations. We put P0 S X T gamma is maybe, I'm sorry, maybe it would be better to write down write the equation in the following form. Denote by U S X T phi this integral. Here S X and phi of X is a bounded measurable function. Okay, then the first equation can be written as follows: U S X T phi equals integral of X phi of Y P S X T dy plus integral tau integral of X P U tau Y P P V tau Y P S X T tau UI. Okay, so we integrate with respect to this measure, some bounded function. Measure function p of x, and we have that equation for this function. And I am going to apply the method of successive approximations to this equation. So I denote by U0 T S X T P equals integral phi of Y P S X T dy. And for K UK S X T P equals integral tau integral U K minus 1 tau Y T phi V tau Y P S X tau dy. Okay, and we have the following estimation: U0, absolute value of U0 is less than norm phi. Norm phi is the supremum of absolute value of phi. Okay, and now induction. I would like to recall our assumption is integral over x, v tau y, p s x tau y is less than. Oh, here is written. It is written here. Okay, so so by induction on K, we have the following estimation. UK S X T is less than or equal to norm phi K T to the power K gamma 1 minus gamma to the power K gamma of N 1 minus gamma plus 1 and T minus S to the power K 1 minus gamma.
Sorry, we need the absolute value, or we need the absolute value of the difference of UK and UK minus 1.
No,
No?
no. My solution will be the sum over all.
Ah, I see. And we need the series to converge. Yeah.
Yes, yes.
Okay.
It is very easy to verify that this estimate is held true for OK. Yeah, okay. I'm sorry. Okay.
Sorry, gamma, there is some other constant or what? Or
Gamma of x is Euler's function.
ah, okay.
Euler's function. Because you see, you have integrate here tau minus s, and this is tau here t minus tau, and here according to this tau minus s. So we have some Euler's function beta, and it can be expressed through Hammer. So you see this series is a convergent one, and it is very easy observation that the solution to this equation is unique, because if you have two bounded solutions to this equation. Then the difference between them satisfies this equation with phi being equal to 0. Okay? So you have that for that difference, this inequality is true for any k Therefore, u is equal to 0. And this series is a solution. And it is a bounded function. Yes, because I can t minus s is less than t. So I have that this series is some constant is equal to some constant is not greater than some constant. So we have constructed a bounded solution. If phi is an indicator, then I have this equation.
And it's like a value of the function, some functional on every bounded measurable functions. Phi, yes, on
Yes.
our space, and we from the values of this functional, we derive the corresponding measure like that.
Yes.
Yeah.
We can put here phi being equal to indicator of the measure.
Mm-hmm.
Okay. And now let us return to the situation where our process is a diffusion process and its transition probability density coincides with the fundamental solution to the corresponding parabolic equation.
So how much time do we have? We should end at 11, or how much time do we have? We should end at 11 or 10:30. We have 15 minutes, like
Okay.
maybe 20 more. Let's.
So GSX TY is a fundamental solution to the following equality. U prime S plus ASX U prime X plus 1/2 trace BSX U second prime XX equals 0. Okay, this is the fundamental solution. We have already seen how to construct such a solution, and we saw how to solve non-homogeneous equation. If we have some function f s x on the right hand side of this symbology, and as a rule we solve we solve this equation with the initial or final condition. This equation is considered for 0 t d. Okay, and a given function. If that function is 0, we know how to solve this problem. U1 can be written as follows. This is integral, the tau integral g s x tau z f tau z is we solve that if f is such that it satisfies it is held a continuous local uniformly with respect to tau, then this function can be twice differentiated with respect to x, and it satisfies exactly this equation and this under some maybe bounded function or something like that. Okay. And now let us write down this equation for this function for this process. So I would like to write down the following: G S X Y dy, and here G S X tau y dy. And first look, let us have a look at this integral. If I denote it this, if I denote this by f tau z tau y, I will have an integral like this one. Okay, so I can purely formal, I can apply this operator to this function, and what we have, u prime s plus a s x u prime x plus 1/2 trace second prime x, and it must be equal to minus this expression. Yes, we write down it here on the left hand side. V S X U equals 0. And if S goes to T, we have ut minus X. Okay, ut minus S X T equals X. You see, if it is true, if I can apply the second derivative to this term, then our solution US XT must satisfy this equation and this final condition. So, and we know what a function U must satisfy this equality. What a function must solve this Cauchy problem. U S X T is equal expectation phi of X of T X integral d tau X of tau d tau, where X of T MST PSX is diffusion. Process corresponding to vector field ASX and operator field BSX. This is the sense of the term the Feynman-Katz formula. This formula, this expectation is a solution to this equation. This is the Kolmogorov backward equation. But if we consider here expectation, so this term arises here in this equality. Okay. And now, but sorry. If V is a smooth function, we can expect that this function, you see here, is an unknown function. This function is to be constructed, to find out, okay? But if it turns out that this function is locally Hilbert continuous, with respect to y. So we have this equation. But if it is not, if v is, for example, if v is not smooth, then we can not write down this equation because here is this equation should be understood in some generalized sense. For example, in this sense, we can believe that this is, if we can construct the solution to this equation, we can believe that this is a generalized solution to this issue problem. Okay. One example is very famous, and it was found out by Mark Katz. 14th. So suppose that we consider one-dimensional Brownian motion. And let V as X be the indicator of our class. It does not depend on S. And our class consists of all X from R. Let R positive. So our function is indicator or plus of X tau d tau. This is the time that our process spends on this semi-axis during the time from S to T. It is very interesting to find out its distribution. I would like to say a few words about how to find out that distribution. So we have this equation for bound measurable function phi. And this time V is the indicator. So I get write down the equation. For where GSXTY is given by the transition probability density of the Brownian motion. And you know that this solution of put phi of x being equal to 1 identical here. So we have the following and denote by this integral by u s x t lambda. Then this equation can be written as follows: 1 plus e lambda integral d tau integral over r plus g s x tau y u tau y t lambda uy.
So y is not equal to what is equal to lambda.
V is equal V of Sx is equal E lambda indicator of X. A phi equals 1. So I put it 1. This is not corresponds to the previous notation. Okay. Okay. US xt lambda. See, and it is not difficult observation that this function is a function of t minus s. It depends on s and t in such a way that it is a function of t minus s. And I denote this new function mu t x lambda, and it is such that if I put here t minus s, I obtain this function. Okay? So for that new function, we have the following equation: u t x lambda equals 1 plus e lambda integral d tau integral this function is also a function of t minus s. Okay, so this is a new notation g tau x y u t minus tau y lambda ui. Okay, and we have here a convolution, the function tau t minus tau. So, you know, by u tilde u tilde p x lambda, the Laplace transform of this function as a function of t. Okay, and I will use the following known formula: integral e to the power minus pt 2 pi t to the power minus 1/2 x minus a square over 2t dt is equal 1 over square root 2 pi e to the power minus absolute value of a. A is a real number.
Sorry, where did we lose p in the first formula? Or u tilde?
Sorry, thank you. This is must be
Thank you.
lambda. Lambda is the other. Okay, thank you. The square root of 2 pi. This formula is true for any complex p with positive real part. How to prove this formula? In the book by Portenko N about diffusion processes. There is an exercise how to prove this formula with the help of integrating in the complex plane. But once I delivered my lessons in our university, and when I told my listeners that how to prove this formula, one of my students on the next lesson handed me another way how to prove this formula. Try to prove this formula. So we take the Laplace transform of this equation. So we obtain the following. 1 plus e lambda integral from 0 to infinity minus absolute value y minus x square root of 2 pi u tilde p y lambda ui. And it is very easy to understand that the function u is twice differentiable at any point other than 0. Moreover, if we can differentiate twice with respect to x, this equality, and we obtain the second order ordinary differential equation on the right hand side of real line and on the left hand side. Okay, and those equations will be with the constant coefficients, and they can be solved. There will be 4 arbitrary constants. They can be found out, and the distribution can be found. I would like can be found if I consider that process, Brownian motion, starting at instant of time 0 from origin, and consider this functional, the probability that this is less than y is equal to 2 over 2 r sine square root of y over t. Y is from 0 to t. This is the famous formula. Though the arc sine law, it was obtained by cuts. There are other ways to obtain this formula. Those ways are known. This formula was known, but cuts obtained this formula from the differential equations. That was very, very effective. So thank you. That's all for today. See you next Tuesday.